It all began with a question that seemed harmless enough. Why do planets move in ellipses? When Johannes Kepler first described the shape of planetary orbits, he had no idea that he was lighting a fuse that would burn for more than 2 centuries. What does it feel like to invent math? During the early 1600s, Kepler studied the motion of planets and in doing so, discovered that certain laws were obeyed. These were his 3 laws of planetary motion, and they helped us understand what was going on in the heavens above. Planets moved in elliptical orbits with the Sun at one foci. Equal areas are swept out in equal times, and the harmonic law connects the orbital periods, and here is the geometry of the ellipse, which was something that the ancient Greeks already knew something about. Algebraically, the ellipse satisfies the equation x squared over a squared plus y squared over b squared equals 1. And a and b are the semi-major axis and the semi-minor axis. But calculus had not been invented yet, and so studying the dynamics on an ellipse was breaking new ground. In calculus notation, Kepler wanted to predict the distance a planet traveled along its elliptical path, leading to the integral of this form where e is the eccentricity, measuring how stretched out the ellipse is from being a circle. From the seeds of Kepler's work, there would be a great deal of mathematics developed, namely giants like Newton, Euler, Gauss, Legendre, and Abel, all extraordinary people who would pave the way for one man to invent a solution by rethinking the question entirely. Standing on the shoulders of giants, this man would prove his genius by inventing a brand new function. Okay, let's take a look at the unit circle. A unit circle is one of radius equal to 1, so therefore it satisfies the equation x squared plus y squared equals 1. A parametrization of the unit circle is given by x equals cosine theta and y equals sine theta through the relationship of the circle and the right triangle. So any point on the unit circle can be parametrized through its angle, and in this case the radius is equal to 1. So how do we calculate the length of an arc? Well, it turns out that using the Pythagorean geometry of a right triangle, we can calculate the length of an arc through a relationship between that arc length and the angle itself. The radius being constant allows the locus of points of a circle to be equidistant from the center at all times. Now if we reparametrize the circle using the complementary angle and focus on the triangle, we get y is equal to the positive square root of 1 minus x squared, which is the upper half part of the circle anyway. And from that we can complete the Pythagorean square here and create a triangle of which we can then write down the sine and the cosine of that triangle. And differentiating these, we get d theta dx to be 1 over the square root of 1 minus x squared. Integrating both sides will allow us to calculate the arc length through the fundamental theorem of calculus. And this integral leads to d theta dx being equal to the derivative of the arc sine of x. So theta equals the arc sine of x. In other words, the inverse of this integral is the sine function. So arc length for a circle with a constant radius means that the angle moves in a uniform fashion, and therefore calculating its integral allows us to use elementary functions. But elliptical paths lead to elliptical integrals. And that's where we have to ask the question, what happens when you stretch a circle? Ever since Copernicus and Galileo, the sun has stood as the center around which all things orbit around in a circle. But what Kepler discovered was that planetary paths were ellipses, largely due to inconsistencies in the circular theory. But what if you split the center of a circle into two focal points, and the radius that used to remain constant is now split into two focal radii of variable length? The sun appearing at one of those focal points, you see by stretching the circle, motion around the ellipse exhibits nonlinear behavior. The once 2 pi periodic behavior has now split somehow, as if there were two circles at work, two clocks, which are not in step. So what happens if we try to calculate the arc length now, where angular speed and arc length speed are not directly correlated? The parametrization for the ellipse can decompose the oscillatory behavior into the x and y directions respectively. The measures of the semi-major axis and the semi-minor axis serve as the focal radii that govern the amplitude of the cosine and the sine functions in the parametrization of the ellipse. So in the parametrization of the ellipse, A and B are different lengths attached to the sine and cosine functions. This way we get two competing periods. The ellipse has two complementary directions of curvature, which does not simplify nicely. It cannot be inverted and cannot be expressed with elementary functions. In other words, the motion along the ellipse is not uniform with respect to angle. Stretching the circle breaks the equivalence between the angle and distance, and so we now have one parameter theta and one arc length s, but no closed form relation between these two variables. You see, on an ellipse, elliptical integrals are trapped on the real number line. Motion decomposes into two competing oscillations, motion along the major axis and motion along the minor axis. The integrals become zero at turning points, motion stalls and reverses, and inverse functions become multi-valued. This is part of the problem in the inversion process. You need a one-to-one correlation. Now, it would be Legendre that completed the work of Euler, classifying the elliptical integrals into three kinds, the first of which are considered here. The first kind is an integral involving a square root, and the second kind also an integral involving a square root, but both of which have some parameter k. Then in the early 1800s, a seemingly poor, unsupported, and brilliant young man by the name of Niels Hendrik Abel showed an aptitude for mathematics. His methods were rooted in questions about principles and laws, and not so much about computation and formula. He worked a hard life with little recognition of his work and his genius, at least not until it was too late. You see, his paper on elliptical integrals outlined the problem of inversion in detail, but when he sent his work to Cauchy and Legendre, it was lost amongst a stack of papers. His papers emphasized the real need to invent new transcendental functions. What Abel did was laid the fundamental groundwork through his transformation laws, which would later form the basis for the study of modular transformations. And Abel also showed that the inverses have periodic behavior in the real sense, but they turn the same value under translation. The multi-valuedness of the periodic behavior led to this idea of double periodicity, two independent periods, an entirely radical idea that had not been considered before. Abel was interested in transformations of the elliptic integrals. He shows that they can be transformed via algebraic substitutions, and he forms the basis for what would later become the study of modular transformations. Abel shows inverses have periodic behavior in the real sense. They return the same value with translation. And multi-valued periodic behavior is implied by his analysis, which lays the groundwork for understanding a concept of double periodicity. And this is where his work ended, as his work would be cut short by his death at the tragic age of 26. Adding to this tragedy would be a letter that he received 2 days before he died, inviting him to become a prestigious professor of mathematics. He never saw the letter. When Abel's work was rediscovered by Legendre and Cauchy, Legendre would bring Abel's work to the attention of another young genius, one that was obsessed with symmetry, periodicity, and exact analytic forms. What Abel had started, this man would finish. If necessity is the mother of invention, this man was the father of inversion. Carl Gustav Jacob Jacobi lived from 1804 to 1851, and he lived a very different life than Abel, one with support and an academic network. When Abel's paper was brought to his attention, it inspired his obsessions with explicit forms and the problem of inversion. Jacobi wanted to invent the elliptic form of the trigonometric functions. So where did he start? Well, with a question about the integral that was so resistant of inversion. And he suspected that it had to do with the nature of double periodicity. Jacobi defines the amplitude function. Phi is equal to the amplitude of u, the amplitude of the angle whose elliptic integral is equal to u. You see, Jacobi would use this to define his elliptic functions as the sine and cosine versions of the ellipse, and define three functions which he would call the elliptic functions, projections of the amplitude. So the amplitude is really just the angle, but an angle that does not move in a linear way, it reacts in a non-linear way. So elliptic motion speed varies, and therefore the angle advances in a non-uniform way. The amplitude function tells you where you are when distance and angle are no longer in agreement. What kind of a function is naturally periodic in two directions. Joseph Fourier in 1824 published his work on how a reasonable periodic function could be decomposed into a superposition of simple sine waves, and that the function could be represented over an interval. A Fourier series function could be inverted through a Fourier integral transform method, which would give the frequencies of those waves. This allowed Fourier to reach fame by solving the heat equation. And it was precisely the idea that Jacobi needed to investigate the double periodic nature of the inverse functions, or the elliptic functions. If Fourier laid the groundwork, Jacobi picked up the pieces and realized its full potential. Jacobi wondered if there's a universal function that would encode his inverse. And Fourier's method seemed to be the exact playground in which Jacobi could realize his vision. This pointed Jacobi in the direction of infinite series evaluations, specifically weighted Gaussian distributions. Jacobi wondered if there would be a universal function that encodes this inverse. Jacobi wondered if there's a universal function that encodes the inverse. He wanted to construct elliptical functions in the same way that Fourier had built circular ones out of exponentials. This pointed him to infinite series evaluations, and his goal was to find a function that is smooth, encodes periodicity, and plays well with differentiation. Such a function actually exists already. It turns out that the Gaussian function f of x equals e to the negative pi x squared has a very powerful property. It reproduces itself under a Fourier transform, and it encodes periodicity. This is gold. Jacobi realizes that if you take a Gaussian, sample it at integer values, points, and sum it symmetrically, you can create a function that has periodicity, regularity, and analytic smoothness. All important features that he's looking for. So then his thought turns to, what if I sum a Gaussian over all of the integers? Well, then this gives us a prototype of what is called the theta function. And that is shown here. And this function is the result of summing Gaussians over a lattice of points in the complex plane. This function would serve as the key to Jacobi's unlocking the potential of the elliptic functions. So let's break down this theta function. The first portion of this e to the pi I n squared tau encodes the lattice geometry, or the background. Tau is the modulus of the shape of the lattice, and this is where modular transformations take action. This term controls convergence and is like a Gaussian dampening factor. It encodes the global topology. The second portion is a plane wave navigating the position on the complex torus. Phase oscillations, local position within a fundamental cell, and shifting this gives the periodicity of the particular fundamental cell, which can be represented as a parallelogram in the complex plane. So we will discover that Jacobi learned that his theta function in the real direction has a period of 1, and is quasi-periodic in a complex direction, which we will denote as tau. These two vectors create a parallelogram, which we will call the fundamental cell or the fundamental domain. And it turns out that the half-period values on this fundamental domain encode the symmetries of the theta function. And this is where Jacobi's genius comes in. He investigates the obsession that he has with symmetry and periodicity in this fundamental lattice. By exploring the various symmetries of his theta function, Jacobi discovered that if he translated his function, that would reveal the periodicity of the function, and this creates a symmetric structure in the form of a parallelogram in the complex plane, one that encodes all of its symmetry properties. Now, one of the things that he had to contend with was a concept of quasi-periodicity in the complex direction. All of his work would be a prelude to things that are called Riemann surfaces. Theta functions live on a torus. You see, theta functions have two independent directions that it can behave on, one real direction period and one complex direction period. For simplicity, the basis has been chosen so that the real period, which the theta function represents as a natural real period, is to be taken as the vector 1 along the real direction. And as we will see, that this particular setup means that our theta function lives on a torus. So now we would ask the natural question of what are the features of our new theta function? What are the features of this lattice structure and the fundamental domain? So this is what the fundamental domain looks like when we choose a complex number in the upper half plane, meaning that its imaginary value is greater than 0, and z is just some complex number. This is the doubly periodic domain that we need. So our basis is the real basis 1 and the complex basis tau. So the parallelogram is our fundamental domain, as we shift the theta function in this domain, we deduce its symmetric properties. There's motion in two directions, one along the equatorial plane and one along the tubular direction, which goes through the hole. Defining double periodicity on this domain, you can infer spin around the torus, or spin around the tube-like structure that the torus presents. Now, shifting the theta function in the real direction by a factor of 1, we get an identity relation that defines the periodicity in the real direction. Theta has a period of 1 in the real direction. So then Jacobi shifts the theta function in the direction of tau. By shifting the function to tau, we realize that there is a quasi-periodic nature to the function. And here what we're doing is completing the square to rewrite the sum in a more natural form, which exhibits or factors out the exponential, which ultimately relates to a phase factor change. So you see, once we shift the theta function by the complex value of tau, and doing a little reindexing of our sum, we will find that this particular shift is almost periodic, making it quasi-periodic. It picks up a phase factor, an exponential term in tau. You can think of this as periodicity with a twist. So the double periodicity happens within the fundamental domain. So then we're naturally led to the question, where do the zeros of this function exist within the lattice? In order to find the zeros of the theta function, Jacobi decides to investigate the theta function at different half-period points to see what the zero structures there would be. This is analogous to what you might do in the trigonometric world. Now, exploring the half-period shifts of the theta function, what is it that we discover? So when we ask, where do the theta functions vanish, we're asking, where does the function equal 0? By exploring the half-period symmetries and simplifying our algebraic calculations with creating something called a gnome, q is equal to the exponential pi I tau, we can simplify our calculations here and see what's really going on when we simplify the calculations in the theta function by shifting it first by 1/2. And by shifting it by 1/2, we pick up an alternating series sign. This later will be designated as theta 4. Now, if we shift by half of tau, what happens is, again, we can complete the square and reformulate this series in terms of q, our gnome, and realize that we will again pick up some phase factor in terms of tau. This function is going to be designated theta 2. Don't worry so much about the ordering of the subscripts. We'll explain that later. Now, if we also shift by half of the value of tau plus 1, we also pick up a phase factor as well as an alternating series term, and that will designate as theta 1. And finally, no shift we'll call the mother function, theta 3, is the theta function itself. And these four functions, all the half-period shifts, each exhibit a certain symmetry of the function. Theta 3 obviously being the identity. So now expressing the theta function, that is tau that lives in the upper half plane, so its imaginary value is greater than 0, means that the gnome q's absolute value is less than 1, and z in the complex plane means that we next consider to reduce the sum down to its parity, meaning are these functions even or odd, since we now have 4 functions to investigate with different symmetric properties. If we pair terms with n with its partner negative n in the series, we can actually change the sum into a cosine sum, in which case we will get this particular shift to indicate an even function. Cosine is an even function in z. So next we investigate what we can do with some of these other functions. So we've got our mother function as an even function. And Jacobi decides to investigate the parity or even or oddness symmetry of each of these variations of the theta function. He discovers that theta 4, which is the shift by 1/2, is something that again can be paired using n and n-1, and so we can reduce the summation down to something that we can identify as either being an even or odd function. And through a little algebraic manipulation, and using the exponential form of sine and cosine again, we get this to be another form of cosine, another even function in z, but one that alternates its sine weights. Theta 2, and that would be equal to the shift half of tau. Again, we can complete the analysis here, and this time we're going to pair n with negative n-1 pairs, and this will help us keep a symmetric value, in which case we can complete the square, and write a sum in which we can evaluate with a trigonometric value. So it turns out again that this particular function, theta 2, is another even function. And here Jacobi's really searching for something that he can represent as a sine function, one that's actually odd. So now we look at the function theta 1, which is a shift by 1 plus tau over 2. And this one is the one that has the alternating sign and also picks up a phase factor. And again, pairing n with negative n-1, we can pair this off and get a sine function to pop out of this. In other words, that theta 1 is an odd function, and thus will help us to find something that is analogous to a sine function in the elliptic world. So since theta 1 at 0 is equal to 0, perfect candidate for that. And this is sort of the breadcrumb, the clue that gives Jacobi the idea that these four functions are the building blocks of the elliptical functions. And that all he needs to do is use these four keys to unlock what he needs to do to construct these elliptic functions from the ground up. At a breakdown of each of these functions, theta 3 is our mother function. The 0 is at no special point. The most symmetric function it's an even function, and it's non-vanishing at 0. Theta 4 twists along the one direction, changes parity under real translation, and its 0 moves to the value of 1/2. It's an even function, but it oscillates between lattice sites. It's anti-periodic in space and periodic in time. For theta 2, the 0 shifts to tau over 2, picks up a phase factor as a tau translation, is an even function, non-zero at z equals 0, and it is sensitive to vertical motion in the lattice. Periodic in space, but anti-periodic in time. And finally, theta 1, which is our odd function, has a 0 at z equals 0 and changes sign under z going to negative z. It twists in both directions and sits at the origin as 0, so it is anti-periodic in both directions. So these are the spices that will be combined to create the exact elliptic functions that Jacobi had hoped for. He just had to use them in a clever way so that they would satisfy the properties that Abel helped lay out. And if we plot the Jacobi theta functions, we see in the complex plane that many of them have not only zeros, but they have poles, some things that we will have to consider in constructing the elliptic functions from the theta functions. Jacobi's goal was to build the analogs of trigonometric functions, otherwise known as the elliptic functions. They must satisfy double periodicity, have controlled zeros and poles, and satisfy the relations such as the ones shown below, ones that Abel was able to work out. But there was no explicit proof, and that's the thing. Jacobi wanted explicit proof. So he fixes tau in the upper half plane and generates 4 functions, theta 1, 2, 3, and 4. Each of these is quasi-periodic, meaning that they contain phase factors that need to, in his opinion, be cancelled out. That is, under these half-period shifts, they pick up explicit exponential factors, which he knows can be cancelled out in a clever way. So what he decides to do is create ratios of these particular functions. Ratios that would explicitly cancel out exponential factors that are picked up. So Jacobi chose ratios that acquire the same phase factor under different shifts. Then the phase cancellation makes the new function doubly periodic. Jacobi looked at the fact that theta 1 was odd and vanishes at 0. It's a perfect sign-like numerator for the ratios he would construct. Theta 4 is even and non-zero at z equals 0, making it a good stabilizing denominator. And theta 2 and theta 3 give other symmetry types which are analogous to cosine-like pieces in this fractured circle, otherwise known as ellipse. The last step after the desired ratios were found is to choose normalization constants using the theta functions, the so-called theta constants, so that the identity relations are satisfied and so that they match the following values. Sn of 0 is 0, and Cn and Dn at 0 are also equal to 1. Using modern notation, one can represent all changes and all shifts in the symmetric directions in vector notation. But to get the constants, what one does is sets z equal to 0. Now, to consider the non-zero theta constants, where we have theta 2, 3, and 4, it turns out that they follow an identity relation themselves, given here, which can be written as 1 equals theta 2 over theta 3 to the 4th plus theta 4 over theta 3 to the 4th. And using this relation, Jacobi decides to define the parameters k squared as the first ratio to the 4th and call this the modulus, and k bar squared being the theta 4 over theta 3 squared as the complementary modulus, so that it reveals the relation that 1 equals k squared plus k bar squared, or that k bar squared is equal to 1 minus k squared, orthogonal directions on what would be known as the torus, which is the lattice construction. Now, why is this parameter important? If you start with the curve y squared given by this and define the integral u given here, then everything is controlled by one parameter k, and of course its complement. Now when we start with a lattice, we get something that is in terms of a complex variable, but in the elliptical integral picture, the curve here has branch points. Thus, the modulus k is encoding the relative position of these branch points. And now, with our definition of these moduli and the complementary moduli, Jacobi now needs to connect the torus coordinate z to the elliptical variable u. Jacobi defines the complete elliptic integral, capital K equal to pi over 2 theta 3 squared evaluated at 0, and its complement shown there, where 2 capital K is the real half period, and 2I K bar, capital K bar, is the imaginary half period, which matches the lattice in the complex plane given by the basis vectors 1 and tau. So there's a one-to-one correspondence between those two basis vectors. Then Jacobi completes the elliptic integral by defining capital K of lowercase k as this integral, where k is the modulus, and also demonstrated in algebraic form here. And he says that this defines how geometry actually stretches time. Now, in Jacobi's construction, he wants to define the amplitude function, which will help define his forms of the elliptic trigonometric functions. And so the inverses, these elliptic functions, can be defined as long as we can define this amplitude function. So Jacobi elliptic functions are doubly periodic with a real period of actual 4k and an imaginary period of 2ik bar, which allows us to form a fundamental lattice in the complex plane given two vectors which will form this lattice, omega 1 and omega 2. That lattice is the complex plane modded out by those vectors, and tau would be I times the complementary capital K divided by the k. The ratio alone determines the conformal class of the torus, and the modular norm q given there helps us to find the theta function, which encodes the aspect ratio of the torus, which means it's measuring how stretched out the imaginary cycle is. In the degenerate limit, lowercase k goes to 1, and therefore the complement goes to 0, capital K goes to infinity, and the complement capital K bar goes to pi over 2. These are independent measuring rods of the two independent directions of the torus, which is a complex surface. Now, aligning the torus coordinate with the elliptical variable, we let z equal u over 2 capital K, which allows us to make a one-to-one correspondence with the z variable on torus and the u variable in the integral world. This is a coordinate bridge between the analytic theta world and the geometric elliptical integral world. So, constructing the sine elliptic function, the Sn of uk, he takes the ratio theta 1 over theta 4 and normalizes it by the constants theta 3 and theta 2. And this gives a simple 0 at z equals 0, creating a sine-like behavior, and in this case the poles are controlled by the numerator. The numerator and denominator pick up the same quasi-periodic factor in the constants, which fixes the amplitude, so the turning points match the elliptical integral normalization. So everything is controlled by the theta function. We then define Cn of u and k as the ratio of theta 2 over theta 4 normalized by the constants theta 4 over theta 2. This is an even function, non-zero at z equals 0, and satisfies Cn of 0 equal to 1. The same denominator as a sine function, so they have shared poles. I should say the elliptic sine function. And then finally, dn of u, k is the ratio of theta 3 over theta 4 normalized by the constants theta 4 over theta 3. Another even function, and satisfies the relation dn of 0 equals 1. The normalization constants encode the complementary modulus k bar and controls motion in the imaginary direction of the torus. With these exact ratios, Jacobi proves the following identities that Abel outlined, and differentiating the elliptic functions yields the following derivative definitions for our elliptic functions. Not only did Jacobi prove his theta functions were the elliptic functions, but he did much more than that. He had done it. He built the inverse functions from the ground up. He invented new math. It was literally groundbreaking. His whole life, Jacobi never stopped working, and the academic expectations placed upon him were strict. Sadly, Jacobi would die at the young age of 46, essentially overworked to death. Jacobi spent most of his life trying to understand patterns that repeat, but never quite return in the same way. In doing so, he found a new way to describe motion, symmetry, and change. One that helped make sense of complexity without chasing every detail. His approach didn't just solve problems, it made them reasonable. Jacobi realized that some problems don't want to be solved piece by piece. They want to be understood as patterns. And once you see the pattern, the problem almost solves itself. Transforming unsolvable integrals into functions with structure, Jacobi revealed that many nonlinear motions don't live on a line or a circle, but on a torus. And he turned repetition into geometry. In a sense, he showed that some of the hardest problems in mathematics weren't hard because they were too complicated, but because we were looking at them all wrong. By changing perspective, he turned endless calculations into structure and symmetry. His work gave mathematics a new language for describing change, one that feels less like force and more like listening. And with that, thanks for watching.